Um, Good evening. I'm Mr. PJ Luvuno, a lecturer for chemistry. I'll be taking you through chemistry N4. We are doing chapter 3 in your textbooks, which is acids and bases. So those will be part 1 of our lesson. The objectives that we are going to cover for this lesson in particular, it is examples of acids and bases, properties of acids and bases, definitions of acids and bases according to Arrhenius, Bronsted Base, and Lewis. And then we are going to look at the strong acids and bases. We are going to discuss the amphoteric acids, the conjugate acid-base pair, and the equilibrium constant. So those, the last two, the conjugate acid-base pair and the equilibrium constant, we are going to discuss in our part 2 of the video. So when we talk about the examples of acids, there are common acids from our household that we know. Your vinegar, that is acetic acid. Some fruits contain acids. So the fruits where you will get your vitamin C, you'll get ascorbic acid. In your oranges and lemons, you get the citric acid. In your grapes, you get the tartaric acid. In the human stomach, there are gastric juices. Those gastric juices are hydrochloric acid. And then in your urine, that's where you get your uric acid. And then the soft drinks that we drink, e.g. your Coca-Cola, your Fanta, your Sprite, etc., they contain carbonic acid. So the properties of acids: 1, they are corrosive. That means they have an ability to burn. For example, if you consider a car battery, it contains a liquid. That liquid that's inside, it is an acid. If it happens that it spills on you, it can actually burn you. And then when we also maybe look at another type of acid, the gastric juices, as I've explained earlier, inside your stomach. Say you have eaten a certain fruit, and now you have too much acid inside you, then you'll feel that heartburn. So that is why we are saying acids are corrosive. And then they have a sour taste. Take your lemon. If you try and squeeze the juice of the lemon, it is sour. So that is a property of an acid. Acids have a pH value that is less than 7 in the pH scale, if you know what I mean. Then if you are doing an experiment, an acid would turn a litmus paper into a red color. So that shows that it is an acid. And then when acids react with water, they form a salt and water. And then the last one, when acids react with metals, they form a hydrogen gas. Right, let us now look at the examples of bases. Your lime water contains calcium hydroxide. Milk of magnesia contains magnesium hydroxide. Many bleaches, soaps, toothpaste, and other cleaning agents, those are your bases. And then the properties of bases, they are also corrosive. They have a soapy film, and then their pH is more than 7, because you know 7 will be neutral. That's where you'll get your water, right? Below 7 you'll get your acids. Above 7 you'll get your bases. So it is between 7.9 to 14. And then if you also do an experiment using a litmus paper, an acid will give you a blue color. So if whenever you do that experiment and then you obtain a blue color, you know that that substance is a base. And then bases contain a hydroxyl ions. So your hydroxyl ions, that is your OH minus. And then when the bases react with acids, they form salt and water. So it is very important for you to know those examples and those properties, because those things are examinable. All right, thank you. Now I want us to define an acid, right? We are going to define an acid according to three guys with their theories. The first one, it is Arrhenius. The second one, it is Bronsted Base. The third one, it is Lewis, right? So what does Arrhenius say about an acid? What is an acid according to Arrhenius? An acid, according to Arrhenius, it is a substance that increases the concentration of hydrogen ions when it reacts, or when the reaction takes place in an aqueous medium, right? So what that basically means is that you need to have this reaction taking place in an aqueous medium or in water. So the reaction takes place in water, and in the process there must be an increase of hydrogen ions, sometimes called protons, right? So I want us to look at this equation. We have our hydrochloric acid reacting with water. Both these are in aqueous solution. Please note that. So because I do not have the program of writing this correctly, I just indicated for you, right? So this will be in aqueous solution. So when you have your hydrochloric acid reacting with water, we'll get your hydroxonium, which means you have now 3 hydrogens here. So because of that, then that tells you that HCl is an acid, because according to the definition, an acid is a substance that increases the concentration of hydrogen ions, right? So now hydrogen ions are now concentrated in your products. So that you must know. And then your chlorine ion will be your salt that is formed, right? I hope you understand. And then Arrhenius base. What does Arrhenius say a base is? A base is a substance that increases the concentration of hydroxyl ions when the reaction takes place in an aqueous solution, right? So again, the reaction must take place in water or in an aqueous medium, right? And then in the process, a hydroxyl ion is formed, right? So the equation that we have again here, we have our potassium hydroxide. So when this potassium hydroxide dissociates, it will give you your potassium ion, and a hydroxyl ion will be formed. So that tells you that potassium hydroxide is a base. So that is what Arrhenius says, or how he defines an acid and a base. Right, let us look at Bronsted Base. What is how does Bronsted Base define an acid, and how does it define a base? So simply put, he says an acid is a proton donor. He says it is a proton donor. So we are going to look at this equation again. We have our hydrochloric acid reacting with water, which is H2O, and then our products it is going to be a hydroxonium again, and then we are going to have chlorine ion as the salt that is formed, right? So what is a proton? A proton, it is this hydrogen ion that gets transferred to the H2O, which is your water, forming a hydroxonium, right? And then we are going to have that salt that is formed. So HCl, your hydrochloric acid, is an acid because it donated a proton or a hydrogen, because it donated that proton or a hydrogen ion, right? But now what I want you to notice here is that the reaction is not confined to an aqueous medium, right? So unlike Arrhenius, the equation, the reaction can take place anywhere, but it is not restricted into that type of medium, right? Let us look at the Bronsted base. A Bronsted base, he simply says that it is a proton acceptor. So again, when we look at this equation here, we have our hydrochloric acid reacting with ammonia, HCl reacting with NH3. The proton will be transferred to ammonia, and then we are going to have NH4, and that salt will be produced, right? So then it tells you that between these two substances in your reactants, HCl is an acid because it, is an acid because it has donated the hydrogen, and then ammonia becomes your base because it has accepted that hydrogen, forming NH4. I hope that is clear, right? Now let us look at Lewis' definition of an acid and a base. So when we talk about Lewis defines an acid in a different way from the two gentlemen we have discussed above, because it says an acid is a substance that accepts a pair of electrons. The other guy said an acid is the one that donates, right? So that's what Bronsted said. And then Arrhenius would say it is that substance that increases the concentration of a hydrogen ion, you see. So that is just one. But now when we talk about Lewis talks about a pair of electrons, you need to note that, and also you need to take note of the fact that Lewis is saying an acid is the one that accepts. So those are the key points you need to notice in this one. And then the equation that I have prepared for you, that's when you have your boron trifluoride reacting with ammonia, which is NH3, and then your product will be NH3BF3. So we are yet to discuss this equation in detail when we are going to be discussing a dative covalent bond later, because you'll realize that boron, because is in group 3, can only form 3 bonds, and those 3 bonds are already formed. There is no space of accepting those electrons, rather. And then when you look at ammonia, as we know has got a lone pair. So those lone pairs are the ones that are shared between these two compounds, right? And then so those are the electrons that are going to be accepted by boron trifluoride in this equation, forming that product that we've got there. So making boron trifluoride an acid because it accepts a pair of electrons. So it is important for you to take note of that. Right. What is a base? He says a base is that substance that donates a pair of electrons. So going back to our example, ammonia in this case is the one that donates a pair of electrons, right? Which means ammonia in this case is an acid, is a base according to Arrhenius. So again, this reaction is not confined in an aqueous medium. So please note that. So now another section I want us to look at, it is the strong acids. It is important then for you to note and to know these acids, because when you go and sit for your exam, you must expect this to be one of the questions at least containing 5 to 6 marks, depending on how the examiner has decided to assess this part of the section. So you know the question might say, arrange these according to their strengths. So you must read these, know the formula, and the formula you must be able to write it correctly, because as I've indicated earlier, I do not have the program with me that can assist me to write this in a correct way. But now you must know which elements and the ratios of those elements. It is very important. So these acids would be your hydrochloric acid, the sulfuric acid. So we are going to later discuss, maybe in part 3 or part 4, chemical bonding. We are going to discuss how does the structure of these substances look like, because it is also very important for you to know, and the examiner will assess that part of the section as well. Right, so you have your hydrochloric acid, sulfuric acid, nitric acid, oxalic acid, sulfurous acid, phosphoric acid, acetic acid, carbonic acid. So some of these acids you saw when we were explaining the examples of acids. And then the bases, again, you would have your sodium hydroxide, potassium hydroxide, magnesium hydroxide, calcium hydroxide, sodium bicarbonate, sodium carbonate, ammonium hydroxide, and ammonia. Right, let us look at the amphoteric substances. Amphoteric substances, it is defined as a substance that can act as an acid in one reaction or a base in another reaction. It is important for you to note that. It's a substance that you'd find that in this particular reaction, it is an acid. But when you look at another reaction, the very same substance, you find that it is a base. For example, we are going to talk about self-ionization of water. You'll find that when water reacts with water, H2O reacting with H2O, it will act as an acid, but at the same time it can act as a base. It acts as a base. It acts as an acid because it donates a proton. It acts as a base because it accepts a proton. So that is what we mean by that. And then an amphoteric substance can donate a proton in one reaction or accept a proton in another reaction. So I've basically explained that. So this definition is given by Bronsted, because now we understand his definition of an acid and his definition of a base. Right, so the examples of amphoteric substances, that would be your ammonia, because when we, okay, it's fine, it's your ammonia, it's zinc oxide, it's beryllium hydroxide, and water are amphoteric substances. And then I have just explained the self-ionization of water. This you must note because it is examinable as well. So when we talk about self-ionization of water, that's when you have your H2O reacting with H2O, and then the product would be a hydroxonium and a hydroxyl. So this H2O donated a proton to H2O, hence we have a hydroxonium H3O plus, and then what was left was an OH minus. So an acid that releases only one okay, so that we are going to also explain. So that is, in short, the self-ionization of in water. So self-ionization of water, please note that. And then again, what you need to know is that an acid that releases only one proton, for example from your hydrochloric acid, is referred to as a monoprotic. So it can be asked, define a monoprotic. You must be able to say that no, a monoprotic is an acid that releases only one proton. Then you can give us that example. And then an acid that can release two or more protons, for example in H2SO4 sulfuric acid, is referred to as a diprotic. 2, it is going to be di. If it is 1, it is going to be mono. And then if it is more than 2, it is going to fall under polyprotic. It will be poly. Poly means many, right? So it will be polyprotic. Please note that. Right. In the next session, we are going to discuss the conjugate acid-base pair. I left that out today because we need maybe enough time to explain that. When we will be explaining that, we'll also discuss the equilibrium constant, Kc, right? And then I would recommend that you read further from your textbooks. You read further from your textbooks. Sorry. You read further from your textbooks, and then you can download some videos on YouTube, and then please go to Google, type acids and bases, and then go to siavula.com. They have a very well packed presentation there for you guys. I know that you are going to really benefit a lot, because some of the information I got also from that website, and then also used your textbook or your study guide. All right, so that is the end of our presentation. Thank you very much.